Alrighty. Sorry. Hi, everyone. Thanks for coming back for the last lecture of the week, if you're on the East Coast on a Friday afternoon. Today we have Justin Hutchinson talking to us from Los Alamos National Laboratory about the National Criticality Experiments Research Center. For a lot of the people in our consortium doing research, we build these systems from concept for the purpose of nuclear nonproliferation and safeguards, for the purpose of measuring special nuclear material, but we can't have this material in our lab. So strong collaborations with scientists like Justin Hutchinson, and also being able to access facilities such as the National Criticality Experiments Research Center located within the device assembly facility are crucial for us to take our concepts and show that they work, and to really spring off. So, and they have a ton of cool experiments. So yeah, I look forward to hearing about them from Justin, and without further ado, take it away.
All right, thanks, Michael. Hopefully you can see and or hear me, at least hear me for sure.
We can see and hear you.
Excellent. So yeah, thanks for that intro, Michael. So as Michael mentioned, I'm here to talk about a lot of the work we've been doing at NSERC, the National Criticality Experiments Research Center. So this is really sort of an overview of just a lot of the exciting work that we're doing these days. And the short version is there's kind of way too much exciting work to talk about in the time that we have. And I'll apologize, these slides are going to be very busy. So that being said, you know, if you try to read every word on every slide, it's not going to work, because I'm going to have to move pretty fast to get through all of this because we have so much exciting work. So that being said, I think this is being recorded. So if, you know, there are things that I just go through way too fast, hopefully you can go back and check them out later, or you can ask me at the end. One thing to mention is that, you know, I'm excited to be here to talk to MTV and the other consortia. And, you know, the student programs are extremely important for us at NSERC, and the team specifically we work in at Los Alamos is the critical experiments team. And everyone on our team, all these people you see here listed, they all came up through the student programs here at Los Alamos through various programs such as these consortia. And so I also want to use this talk as a way to sort of highlight a lot of the exciting research that our students are doing right now here at Los Alamos. I say at Los Alamos and not in Los Alamos, since we're only doing virtual internships this summer. But that being said, yes, there's a lot of really exciting work happening. So yeah, I'll kick it off. So this sort of shows an overview of some of the history of critical experiments that happened at Los Alamos. So really, you can trace critical experiments all the way back to the very beginning during the Manhattan Project. So during the Manhattan Project, there were lots of different experiments, and we certainly don't have time to go over all of them today. Some of those, the bigger ones included the Dragon experiment, which you may have heard of. It was kind of the first fast burst assembly ever, and it was a really exciting experiment. I'll show a picture of it on the next slide, as well as the water boilers. And there were lots of other critical experiments also during the Manhattan Project. So then one of the things that happened very shortly after the Manhattan Project, this happened on August 21st, 1945. So just slightly after the war had ended, there was a criticality accident. It was essentially the first criticality accident, and it involved a fatality, a man by the name of Harold Daghlian. And so it was sort of from that accident and a subsequent accident that happened in 1946 that it was decided that, you know, we can't be doing these types of experiments by hand because of the risks. So it was from that and from those early criticality accidents in which, unfortunately, there were fatalities, that it was decided to start up this critical experiments capability. And so from that, there was what was called the Pajarito site, and later renamed to the Los Alamos Critical Experiments Facility, that was in Los Alamos and operated from 1946 until about 2004 or so. And there were many, many exciting experiments. And unfortunately, I can't really talk about them today just due to time. So then we shipped the material from T18 in Los Alamos out, as Michael mentioned, to the device assembly facility in Nevada. So those shipments kind of happened in the early 2000s. And in 2007 is when we first started doing the first subcritical experiments at the DAF. And then in 2011 is when we were able to start back up our critical experiments capability. And that's when NSERC was officially founded. And then the last kind of step in the startup of the new capability was the Godiva 4 assembly, which I'm going to talk about. And the first burst occurred in 2013. And at that point in 2013, we were essentially fully up and running. So to talk a little bit more about the history, this slide shows some of the historical experiments that were done. So on the far right there, that is the Dragon experiment. And again, I don't have time to go into this in too much detail, but basically they were dropping a slug of uranium through some rings of uranium. And so it was essentially the world's first fast burst reactor. And it was the first time ever when anything went super prompt critical. So it was critical on prompt neutrons alone. So that was obviously a very exciting experiment. There's a nice write-up I can refer people to on that experiment. Another experiment, which I don't know if you can see my mouse here. Yeah, it looks like you can. Sort of in the bottom middle here, that's the Jezebel experiment. That was the first bare plutonium critical experiment, and it's sort of the main experiment still used for validation of plutonium nuclear data to this day. The bottom left is the original Lady Godiva experiment. So it's quite similar. It's a bare sphere. In this case, it's of highly enriched uranium, and it's the primary experiment used for uranium-235 nuclear data validation to this day. The top left picture is this same experiment, the Godiva experiment. It's actually, in this picture, raised up in the air by two telephone poles, and it's raised about 15 or 20 feet in the air. To me, this is one of the greatest pictures of any experiment that Los Alamos has ever done. I think it's so cool. And, you know, I think that to this day, we do a lot of really fun and cool experiments that I'm going to talk to you about today. And I hope that, you know, all of our students and staff members get to do lots of great experiments. But to me, that picture is really the pinnacle of anything that is fun that the national labs have ever done. I don't know that we will ever be able to top that. So to me, that one's kind of the top. So now to talk about the work that we're up to today. As Michael mentioned, the work we're doing is at NSERC, which is the National Criticality Experiments Research Center. So NSERC is our capability of critical and subcritical experiments, which is located inside the device assembly facility. As Michael mentioned, the device assembly facility is out at the Nevada National Security Site, which used to be called the Nevada Test Site. So you can see the picture of it there in the right. It's basically a large facility out in the middle of the desert. And yeah, there's not much around it really. So really our statement is that we want to be able to perform critical and subcritical experiments and even super prompt critical experiments that I'll talk about with Godiva. We're the only general purpose critical experiments facility in the US and one of the very few that remain throughout the world. Basically, if you go back way in time, many different facilities used to have their own critical experiments capabilities. And part of the reason behind that was because there was very few simulation capabilities that existed. So if you wanted to do some process, most processing facilities in the US had their own critical experiments facility as well. So they would want to do a process, they would first design an experiment, they would show through the use of experiment that they could do that process, and then they would execute the process. But through time, simulations became more and more prevalent and more accurate, so they started sort of replacing some of these measurements, and also it became much more expensive from a security perspective So because of all of that, and because of nonproliferation, essentially all of these facilities started shutting down, and we're really the only facility that's left that does this type of work. Now, that being said, we're not trying to say that there isn't great research being done in these kind of fields at other facilities. There's lots of great research being done at research reactors and other types of facilities, as you all know. We're just the only one that can do this type of research with high quantities of special nuclear material. And we'll show what a lot of those experiments look like here in just a second. So we have 4 different critical assembly machines, and this slide sort of goes over some of the types of experiments we do, but I'm not going to spend much time on this because we're going to go into all of these in detail. In addition to our 4 critical assembly machines, we also do lots of hands-on subcritical experiments, and we'll be talking about those in detail as well. So to start off, Planet is a machine that we have that is a vertical lift assembly machine, and you can see it best in the second picture on this slide. And basically, the way Planet works is it's very simple. There's a stationary platform at the top, and then there's a movable platform at the bottom. And what we do is we build the experiment from scratch. So oftentimes, we might not even start off on the machine. We might just start building the experiment on something like a cart, and we will do an approach to critical. This approach to critical is the same methodology that was used by Enrico Fermi in 1943, or I think 42, sorry, when he was doing the Chicago pile experiments. So we use that exact same approach to critical methodology, and we're basically building the assembly by hand, which in my opinion is extremely fun. You have lots of simulations to sort of guide you to know where you think the experiment's going to go. But that being said, those experiments are not going to be perfectly accurate. And that's the whole reason you're doing the experiment in the first place, right? To try to understand more about these systems. And so oftentimes as you're kind of building these assemblies, you will be learning things about the assembly as you proceed with the build. But it's done in a very slow and controlled manner such that we can really get there in a safe way. And so in my opinion, it's extremely exciting to do these types of experiments. So a few examples on the far left here, you have the class Wells experiment. This is basically an experiment where we have thin HEU that we can moderate and get down to very low critical mass. And then on the right side, there's just lots of other experiments we've done. The second one is collaboration with Livermore that involves weapons grade plutonium plates. And then the other 2 here related to plutonium oxide experiments that we've done as well. So an upcoming experiment that we're pretty excited about is related to yttrium hydride. So yttrium hydride is of interest to the microreactor community, mostly due to the temperature effects associated with yttrium hydride and the fact that it can go up to these very high temperatures that would be of use in microreactors. So we're doing an experiment very soon on Planet. And again, I can't really go into the details because we have lots of exciting experiments to get through, but we do have an upcoming experiment on Planet related to this application. Another one that I'm really excited about is called the music experiment. And the music experiment, it basically looks at starting from a very, very subcritical system. So we have a very small sphere of HEU, and then we just start growing that sphere of HEU up until a critical configuration. And along the way, we're going to take lots of measurements with many different detector systems. This slide lists 3 detector systems, but in reality, we're hoping to use up to 5 different detector systems. And that's partially in collaboration with Michael as well, who will be using one of those 5 detector systems. So we're hoping to use 3 different helium-3 based systems and 2 organic scintillator based systems. And to me, this experiment is really exciting because we've never really looked at this large range of criticality before on the same system, which is a very, very simple system. and really looked at what do our various methods look like for different types of detector systems. So this will really help drive home the differences in both our methodology as well as our detector technology as we try to estimate various parameters about the system. One thing I'd like to mention is that a lot of the design for this experiment is being done by the latest member of our team, Rob Weldon, who's a postdoc that was formerly a CVT student during his time. Sorry. So our next critical assembly machine I'm going to talk about is Comet. So Comet is very, very similar to Planet. You still have a stationary platform as well as a movable platform. The difference between Planet and Comet is Comet can allow for experiments that weigh a lot more. And you can kind of see in this picture on the bottom right that this assembly weighs a lot. So we have almost 20,000 pounds between the copper and the HEU in this system on the bottom right. Some of the recent experiments we've done on Comet are in collaboration with the JEA, and they're very interested in lead because they're doing work for accelerator-driven systems that use a lead bismuth eutectic coolant. And so part of the interest of this is to really try to understand lead cross-sections better. And so we've actually done 4 different experimental campaigns related to that. One is an HEU system, one's an LEU system, one's a weapons grade plutonium system, and then one is a reactor grade plutonium system. So this has been a really exciting collaboration that we've done with JEA to help look into these lead cross sections. Another experiment that's been done on the Comet assembly, which some of you may have heard about, is the Krusty experiment. So Krusty is to support NASA operations. The idea here is if we want to go to the moon again and then eventually go to Mars, space nuclear power can really greatly help with that. And so there's a lot of research being done on space nuclear power because of that. So here on the right side, you can see both the kilopower prototype, which is the one that would actually fly, and you can see on the far right our Krusty experiment that we demonstrated at NSERC. And very, very recently, I think just 2 or 3 weeks ago, we had a special issue of Nuclear Technology come out that has 8 different technical papers on Krusty. So if you're interested in learning more about that, I definitely recommend you check out this issue. So yeah, to show you a little bit more about what Krusty is, it's an HEU core surrounded by beryllium oxide and steel, and you can see what the fuel looks like there, as well as the white in the 2 bottom pictures of the beryllium oxide. We did lots of different experiments, 117 total different configurations over several months, and some of those are going into the ICSBEP, which is basically a repository of criticality experiment benchmarks. Some of our simulations were done by one of our students, Kristen Smith, from Texas A&M. And this shows some of the data from Krusty, which has been very, very exciting. So after we did those sort of 117 configurations, the last configuration was the full power demonstration. And so the full power demonstration lasted for a total of 28 hours, as you can see on the x-axis in this plot here. And the sort of top band of data is related to the reactor temperature, which goes to the left y-axis, and the bottom band of data is related to the power in the system, which goes along with the right y-axis. Obviously, I could spend an hour just talking about this plot. There's a lot going on here. But this is a really exciting experiment. You can see that we were at or around 800 degrees Celsius for the majority of this experiment, which is sort of outside the bounds of what we had typically done at NSERC up until that time. Most of our experiments had been sort of 300 degrees Celsius or less. And the exciting thing is the point of this demonstration was to really look at different transients to see how would the reactor behave if there was a failure, for instance. And so a lot of these different things we're looking at these types of failures. And what was demonstrated is that this is really a load following system, which means that even if there were various different types of accidents or not accidents per se, but types of failures, that the reactor would be okay and could still output the needed power. And it also helped show that it can basically provide power on demand, which is very useful not only for space applications, but also for other microreactor applications. So last, another experiment on Comet is called the Curie experiment. This is designed to help with the unresolved resonance region in uranium-235. And this experiment is sort of our most recent experiment, as you can see, executed on Comet in June and July. They actually just finished the Curie experiment yesterday. So it's very, very recent. It's quite similar to the other Comet designs though, so I'm not gonna show this too much other than stress that, again, related to our student programs, both the preliminary and final design of this experiment were greatly helped by students that we had in previous summers. So our third critical assembly is flat top. So unlike Comet and Planet, these last two assemblies are going to be much more specific and not sort of general purpose. So flat top uses one of two cores. One is 17.7 kilograms of HEU. The other is 6 kilograms of weapons grade plutonium. And it's reflected by 1,000 kilograms of natural uranium. And so from this, we can do lots of different types of experiments. It has a hole that goes through the center of the core, so we can do things like full irradiations or fission chamber measurements with flat top. And then our last critical assembly is Godiva 4. And Godiva 4 is kind of the most exciting. It's our only super prompt critical machine. So it's a fast burst reactor, only one of two fast burst reactors left in the US. It's 65 kilograms of HEU. And from that, we can generate a super prompt critical burst. And you can see the theoretical max here. In reality, our practical max is more like 250 degrees Celsius, but it still generates a lot of neutrons on the order of 10 to the 16th neutrons. And it's really a criticality accident that is controlled. So it's really exciting to be able to see, since it is a controlled criticality accident, you get to see what that would be like and what types of radiation doses would be produced and what other types of effects would happen. So it's quite exciting. And then in addition to that, as I mentioned, we also do lots of subcritical hands-on operations. So these are called RTO operations, which stands for Radiation Test Object. And we do these primarily for the sake of detector testing. So if folks have different technologies they want to test out, they can come and test them out, as Michael mentioned, on actual nuclear material. And we do that, of course, in collaboration with universities, which the bottom right picture there is related to some of the university measurements that I'll talk about later. And we've also done that for other sponsors as well. So we do, as I mentioned, lots of experiments that are these subcritical experiments. And these also get published in the ICSBEP, the Criticality Experiment Handbook. And we've been trying to grow that specifically for our subcritical experiments and our subcritical experiment capabilities through the years. And this just shows some of our recent experiments. Our most recent experiment is called NESO, which stands for Neptunium Subcritical Observations, which also happens to be the name of the 13th moon of Neptune. And the NESO experiment used our Neptunium sphere, which is 6 kilograms of Neptunium-237, and is, to our knowledge, the world's largest single piece of Neptunium-237. So we recently did experiments with that, and we're now analyzing those results and trying to do a benchmark for those experiments right now. One of our students this summer, Mariah Ramirez, who's also associated with NSSC, is looking into this and trying to help us out with some of the analysis associated with this experiment. In addition to that, we have lots of students who are exploring various types of R&D associated with some of these subcritical experiments. So 3 of them are listed here, and they're looking at different types of simulations primarily to help us to really be able to understand our results better and to improve our capabilities at the same time. In addition, we've done, as I said, many different experiments with the universities. And so one example is shown here that involves 3 students that we collaborate closely with from University of Michigan that are all MTV students. So Michael, as well as Noah Kleeke and Kaiser Bravo, who are both doing work with us this summer. So you can see pictures here of some of the measurements that they did with an organic scintillator system for Rossi alpha experiments. So you can see, as I mentioned, we do lots of what we call benchmarks, and we have lots of upcoming benchmarks, which are shown in this table in the bottom right. And these will really show in great detail all of the full analysis associated with these various experiments. And in addition to that, one thing to mention, I talked about at the beginning that 2011 is when we started up our operations at NSERC. So we're coming up here on the 10-year anniversary for NSERC in 2021. And so for that, we're hoping to really summarize a lot of the work we did in the first 10 years of experiments at NSERC. So in order to do that, we're going to put together 5 different papers. We have 1 per machine plus RTOs. So you can see the names here. I forgot to list the RTO paper, which is being done by Ernesto Ordonez from Texas A&M, but you can see that we're actively trying to really document a lot of this. Some of it hasn't been so well documented in the past, unfortunately. So we're trying to improve upon that. There is a really interesting paper, especially if you're interested in sort of the history of critical experiments. And that paper shown on the bottom right, it was called The End of an Era, and it was related to all of the experiments that were done at the Los Alamos Critical Experiments Facility from 1946 to 2004. The reason I mention this is our new papers will be called The Beginning of a New Era, in which we talk about the start of all these new NSERC operations. So another thing that I'm really excited to talk about is that we're also doing a project that we'll be starting up very soon called Euclid. Euclid stands for Experiments Underpinned by Computational Learning to Improve Nuclear Data. And so the idea behind this, and this is part of Los Alamos LDRD, the idea behind this is to really be able to really maximally improve applications through the use of our experiments. And so essentially what we have here is that we're going to do experiments. They include not only critical experiments, but also lots of other methods to help reduce compensating errors within nuclear data. And I can't really go into this in too much detail, but in the bottom right, this is an example for the Jezebel critical assembly. As I mentioned, that was the first bare plutonium experiment. And what this plot shows is that if you kind of eyeball and look at these red and blue lines together, you would see that they kind of balance each other out. The total amount of red, or the magnitude of the red and the magnitude of the blue, sort of balance each other out. And these are results from 2 different cross-section libraries. So what that means is if you use only NDEF data, which is the latest US nuclear data library, or you use only JEF data, which is the latest European nuclear data library, the results would be very similar and they would both agree with the experiment well. But if you dig a little bit deeper and you look at how they differ for specific reactions, you can see that these results are very, very different. For the inelastic scattering one, you can see that huge arrow. They're very different. And that means that those differences could have big impacts on other types of applications. So we're trying to not only meet application needs, but also hopefully reduce those compensating errors at the same time. And so the way we're doing that is through the use of machine learning. So part of that relates to the experiment, and we're trying to optimize the experiment. In the center here, this is just one example, and I'll show more on the next slide, in which we have a contour plot for different parameters, in this case, 2 different dimensions of a system. And then this relates to a similarity coefficient that we've defined to a specific application. So we can use that to really guide the design of our experiments. The other thing we're using machine learning for is to help guide in the nuclear data adjustment process. And the picture in the bottom left here shows an example where machine learning was able to be used to find a discrepancy in existing nuclear data that has since been fixed through the use of machine learning again. So one example here that I'll try to show is there's a little movie. So this was made by one of our students, Noah Kleeke from University of Michigan. And this again is just showing this experiment design. So we're trying to advance upon our current capabilities in this experiment design optimization and get to an even better point to help really design these experiments the best way possible. And the reason that's really important is, as you can probably imagine, and you've sort of gathered from these slides, doing these experiments is quite expensive. It takes a lot of people, and even just stepping into the facility is quite expensive. So that's why we really want to maximize the impact these experiments have for various applications. So you might be wondering, I've talked a lot about critical experiments and benchmarks and things like that. And so I think it's sort of natural to think about, well, how does any of this actually tie to non-proliferation in the first place, right? Obviously, one of the main focuses for MTV and all of the consortia and NA22 is related to non-proliferation, right? And so I think it's a natural question to ask, maybe that sounds fun that you're doing critical experiments, but I don't really see a tie to non-proliferation. So basically, here you see what you might think of a little bit more typically as far as proliferation and sort of what happens along the chain. And most of the R&D that probably most of you are working on this summer and throughout your research as a student is related to these types of activities. But essentially, the benchmarks help improve our predictive simulations that we use in all of these efforts. And so, for example, one typical example we often use is you have some box and you want to know what's in the box. And so that applies, of course, to non-proliferation as well as other things. So, on the crit safety side, can I handle the material that's in this box, right? Or is it going to be supercritical if I attempt to handle the material? From the non-proliferation side, has someone diverted material from this box that's subject to safeguards in a fuel cycle facility? Emergency response, is the thing in this box a threat? So to answer really pretty much any of those questions, you often are going to do some combination of experiments and simulations. Or if you're only using measurements, your measurements were often validated in the first place by other experiments and simulations as well, right? And so these benchmarks are really a major part to help with all of that validation in the first place. So the goal is that you are using various codes for your predictive capabilities, and those codes are only going to be as good as the nuclear data that goes into those codes. And so it's through all of these types of efforts I'm talking about that we are really trying to improve upon that nuclear data that feeds into those codes, and then we'll also have sort of this really positive impact on our applications. So this table shows what we call the nuclear data pipeline. And folks may have seen this in various forums. I've probably seen 10 or 20 different types of examples of this plot in the bottom left here. But basically what we have is on the left, we have what we call differential experiments. Those are done at an accelerator facility. So those of you that are familiar with For instance, Lance at Los Alamos, that's one example of an accelerator facility, although there are many others across the country and the world. So we have differential experiments in theory that come in on the left. Then an evaluation is performed that sort of tries to resolve the issues associated with those when you have maybe theory that doesn't agree with your experiment, or you have different experiments that don't agree with each other. Then we process that nuclear data. And then after we process that nuclear data, we try to validate it. And the primary way we validate it right now is through these critical experiments. And so the critical experiments are sort of the primary validation that we are using for the nuclear data. Then a general purpose library is created. So one example of a general purpose library would be NDEF. So if you've ever used NDEF cross-sections, that's the general purpose library. And then sometimes an adjusted library is created, but not as often. And then you use that data for your application simulations. So as you can see, that's where that sort of fits into this larger non-proliferation puzzle. It's through the use of this nuclear data. And everything I've been talking about today, for the most part, sort of goes to that very bottom part related to these, what I'll call criticality experiments for validation and verification. So all the various types of experiments I've been talking about really feed into this validation piece. So one thing you might think is that, we've been doing these experiments, as I mentioned, all the way back to the Manhattan Project. So 75 plus years, we've been doing these experiments, and many thousands of experiments have been done. So you might kind of think, well, we're done, right? I mean, we've been doing this for 75 plus years. All of our data has to be really good by this point, right? So the short answer is, while we have done lots of work to compare these experiments and simulations, as you can see on this slide, we are very, very far from done. There are many gaps. So this plot on the left is just looking at total cross sections for lots of different nuclides, and it's showing the number of benchmarks that are sensitive to those nuclides. And there's tons of gaps, as you can see. There's a lot of white on this slide. Now, that being said, a lot of these things have perhaps very short half-life and have no real implications for any applications that we're talking about in non-proliferation or in nuclear energy or in crit safety, or you name it. No one really cares about them per se. But there are still gaps for applications that we care about as well. So I'm not trying to say that this type of plot really shows you what you need to know. You need to dive in much deeper. But tools like this are useful to help us dive in deeper and help us figure out what are some of these gaps that we're missing. So one other thing that we do a lot of at NSERC is related to education. So we do lots of various courses, and a lot of those really focus on criticality safety. And you can imagine the fact that we're doing all of these experiments that use very large quantities of nuclear material. You should not be doing experiments like that unless you have a really good grasp of criticality safety and you understand, what the results will be on the actions you're taking for these types of experiments. So because of that, we've done lots of research in that area, and we do provide courses, and it's really nice to be able to demonstrate, through the use of live experiments, how some of these parameters of criticality really work. And so we do that both for criticality safety engineers across the complex, as well as for PF4 operators and for other types of students as well. And we've also been very involved with the university consortia as well. And so this slide highlights some of the work that we did for the previous university consortia before MTV existed. This was for the CBT and CNEC consortia. And so we performed measurements for all 5 years of those consortia, and it was largely based upon building these radiation test objects and doing subcritical experiments. And you can see lots of different pictures here of some of these experiments that we conducted over those 5 years. We also did a couple Godiva bursts, but unfortunately I don't have a picture of that on this slide. So you can see here that we did, about 40 different experiments with 40 students and postdocs. And we built over 100 configurations, and there's probably around 20 or hopefully more publications that came out of this. Honestly, I haven't done a good job trying to really find them all, but there was sort of 18 that were low hanging. So in my opinion, this was, like Michael was saying, a really great opportunity. Students don't often get the opportunity to do measurements with large quantities of nuclear material. And to me, this is really a great opportunity, and I'm glad that NH22 has been very supportive of this, to be able to give students this opportunity to perform measurements on these large quantities of nuclear material. And I think it has had really great benefits on their research. So that being said, we're very interested in doing this same sort of thing under the current consortia of MTV, ETI, and NSSC. We were hoping to do some measurements this past summer, but because of all of the coronavirus issues, that's sort of been put on hold. We are still hoping to do those measurements soon, but I guess we'll see how things go with coronavirus. But regardless of that, certainly in the out years, we're very interested in doing experiments. So I know some of you out there probably have very interesting ideas for different experiments. And, if the technology you're working on or any of the research you're working on could benefit from measurements on special nuclear material, we would definitely like to know about that. And we would like to try to help you perhaps perform an experiment related to your research. One other thing related to the consortia is we also have the Keep-In program at Los Alamos. So many of you have probably heard of the Keep-In program. Some of you are maybe part of the Keep-In program this summer. So typically it's 8 weeks in Los Alamos. Of course, this year it's being done virtually. And it includes various technical talks, tours, and workshops. And we sort of top that off at the very end with a one-day workshop at NSERC. There, students get to handle actual nuclear material, including the burp ball. Sorry, I don't know what happened to the slides. Including both the burp ball and the Neptunium sphere that I mentioned, as well as seeing a free run on the flat top critical assembly machine. A free run basically means it's a criticality accident in slow motion. So it's really cool because you get to see all of the different physics effects associated with the criticality experiment, but it takes place over, 10 minutes or so instead of taking place in microseconds. So you get to really appreciate it a lot more. We were hoping to do a Keep-In workshop at the end of this summer. That again was held off due to coronavirus. We're still hoping to do that with this summer's Keep-In students sometime next year. Maybe it'll be kind of a reunion for you guys. Hopefully that'll be fun. So we're still hoping to do that at some point for sure. All right, so I know that was a lot in a very short period of time. That being said, I just want to thank the NCSP program. The NCSP program is really the backbone of everything that happens at NSERC and really helps support all of our various research. And then part of the work that I talked about here, as I mentioned, was part of our LDRD work. So hopefully we have a few minutes here and I can answer some questions. As I mentioned, I know this is kind of way too much for a talk, but hopefully you can feel free to ask me questions afterwards and I can talk in a lot more detail on any of these experiments.
Awesome. Thanks, Jessen. If people have questions, please continue to put them in the chat and I can read them out. One that's in there is back on slide 16. The question is, what is the simulation tool?
Hopefully I can get to slide 16. So sorry, what was the question?
It's what is the simulation tool?
Yeah, I'm not exactly sure what they mean by simulation pool per se. Related to Godiva itself, there have been lots of various simulations that have been done through the years. There is a benchmark associated with the Godiva experiment, and that used just MCMP and was sort of static positions, right? But there's also been some, dynamic simulations that have been done with Godiva. The dynamic simulations that have been done with Godiva have mostly been using sort of in-house Los Alamos tools that unfortunately, in my opinion, haven't really been properly maintained nor documented nor distributed to the public. There are other codes that I know folks have looked into that, have done that type of research, those types of dynamic simulations. So I know a name of a handful of those types of codes, but honestly, I'm not sure if they've actually been tested on Godiva or not.
Cool. And then I guess, have you ever used the Beam NRC or the Gate Monte Carlo codes?
No, we have not used those codes. That being said, we are always interested in results for various codes and how they compare to our benchmarks. So in our team, we probably do not have the resources to necessarily do those types of simulations. But if folks are out there and they're interested in having sort of a validation experiment for whatever type of code they're either an author on or just interested in or like using or whatever, we are always interested in having additional results to compare to.
Cool. A question from myself is, I've seen it in the news, including in the Washington Post, that Nevada has banned plutonium in their state. And I saw that the administrator, Lisa Gordon-Haggerty, promised to remove said material. Does that affect operations at NSERC, or does it affect you at all?
So does it affect us at all? The short answer is yes. And part of the reason it affects us, right, is even though we are, as I mentioned, the only facility in the US that can do these types of experiments with this type of material, it doesn't mean we're the only facility in the US left with that type of material, period. There are other places in which material is just being stored for long periods of time. We are interested in getting some of that material to the DAF for future experiments, and a ban such as that, would prevent us from being able to ship new material in. So does it affect us? Yes, it already affects us right now. If they got even more serious and said they were trying to remove it all from the state, and they did get enough backing to do that, of course, that would dramatically hinder our capabilities. But that being said, that would be a very hard problem because obviously security for this type of material is very difficult. And so given that it is quite difficult, you would have to figure out where you would send it and, who would want to accept it and those types of things.
Got it, thanks. A question in the chat. Is it fair to say criticality is a function of the amount of special nuclear material within a given volume?
So criticality is certainly affected by that. I don't know that I would necessarily define the word criticality as that, but certainly yes, it is affected by the amount of material in a given volume. Yeah, I'm not sure if that fully answered the question.
Yeah, if there's a follow-up, Jake, just feel free to put it in the chat. I guess a question for me on outlook for NSERC. So you clearly have a ton of cool material, the uranium, plutonium, and neptunium, but these benchmarks, are the benchmarks aimed at improving like data for special nuclear material or other nuclear material, or is it these other, I know you mentioned lead, are you looking at lead cross-sections, reflector cross-sections? What is the focus going forward?
So I would say, the focus is really related to what is impacting applications the most, right? And so the various things affecting applications are going to be different for different types of applications. So of course, for example, the things affecting criticality safety applications might be very different from nuclear energy, which would also be different from non-proliferation. So on the one hand, I would say that there is some truth to the fact that do we understand the special nuclear material cross-sections probably better than some of these other kind of interstitial materials? The answer to that is traditionally yes, right? Because the DOE, in our 75 plus years, has invested a lot of resources into understanding, specifically uranium-235 and plutonium-239 really well, right? And so because of that, of course, there might be more low-hanging fruit related to other more exotic materials, lead being one of them, yttrium hydride certainly being one of them, and there's many others that we're interested in as well. That being said, we definitely cannot say, and probably could never say, that we're done learning about uranium and plutonium, right? There's still so much more to learn there related to those.
Got it, thank you. A question from John in the chat is, you mentioned rocky flat shells. Are they actually from rocky flats?
Yes, indeed. So when I talked about how, if you go way back in time, all of these different facilities had their own experimental capabilities. Rocky Flats, in addition to being a production plant, which is probably where folks here know the name Rocky Flats from, Rocky Flats also had its own critical experiments capability. And so these shells were from Rocky Flats. They had nothing to do with the processing that happened at Rocky Flats. They had to do with specific experiments they were conducting there. And then after Rocky Flats shut down, we inherited all that material, or perhaps we inherited it even before then. I'm not exactly sure of the history, but yes, they are called that because they came from Rocky Flats.
Cool. I guess a question in a different application space is, does NSERC, I'll say, support the health physics side, or specifically radiotherapy?
So the short answer to that is yes, absolutely. So both related to Godiva experiments and flat top experiments. We've done a decent amount of work in collaboration with other institutions related to this exact topic. So one thing we've done is we will take various dosimeters, you name it, and we've had a measurement, and we'll basically set up stands where the stand will just have every single dosimeter right next to each other. and sometimes we have phantoms as well. And we'll set up dosimetry on all of those, and then we'll either do a high power run on flat top, or we'll do a burst on Godiva, and then we'll go retrieve that material, ideally, fairly close after the measurements have been done, because some of these things related to like nuclear accident dosimeters, you have to do foil counting. And for foil counting, you need the material sooner rather than later due to the half-lives associated with the foils, right? So we go retrieve that material quickly and then get it shipped off for analysis. So we have done some of that type of work. I would mention, in case there's anyone out there watching, related to some of the MTV and ETI projects I've seen have been related to biota and things like that. In my opinion, something like a Godiva burst might be a good way to test some of those capabilities, because you can generate a very large number of neutrons in a very small period of time.
Cool. Yeah, I kind of makes me think of boron neutron capture therapy as well. We are at 4, so if participants do need to go, thanks for coming, and see you next week. Justin, there was one more question. Do you have a moment to answer it?
Yeah, sure.
Cool. So Jake followed up and asked if you could describe criticality, or maybe give your explanation or definition.
Sure. So basically, criticality itself is just a measure of the state of reactivity of the system. When we talk about it in the context of criticality safety is really the art of preventing a criticality accident ahead of time. But when we talk about criticality in general, it could be any reactivity. It could be a subcritical, critical, or supercritical system. So when we're sort of talking about criticality experiments, really we're talking about anything in that whole range, and it's really just a measure of the reactivity state of the system. Now, I guess the far end of that, if you're at a multiplication of 1, I guess technically that is on that spectrum, but we would never consider like source measurements, related to criticality measurements.
When you do your critical experiments at NSERC, so I mean, I feel like it's very easy to go super critical if you move things a little bit closer, or they got smushed a little bit, or maybe the humidity in the room was different. So how do you prevent nuclear accidents as you're doing experiments?
Yeah, that's a really good question. So as I mentioned, a lot of this was sort of initially established even during CP1, but then the approach that we use was really refined through different criticality experiments that happened. So the idea was, different accidents would happen and we would learn from those accidents. And then those accidents sort of formed the basis for the safety standards that we use today, right? Which are the ANS series standards. And so the general idea, I mean, I can't go into it all, but the general idea is that we're ensuring 2 things whenever we make a change. One, we're ensuring that the step we take is never that large. So there's a rule called the halfway rule. It basically means you don't want to exceed half of the distance from where you are now to where critical is. That's a little vague because that could be in relation to anything. It could be in relation to the mass of nuclear material in the system. It could be related to reflector thickness. It could be related to control rod position. But the bottom line is you want to be able to estimate where critical is and make sure that your step towards critical is never very big. So that's kind of the one major role. The other major philosophy in the approach is related to ensuring that regardless of how big any single step is, once we get to a certain place, we have to stop doing hands-on operations and transition to remote operations. And that's done to ensure that if there was some sort of accident, you know, a person falls on the core, for instance, which is one that comes to mind when I'm looking at Godiva here, because Godiva has 55 kilograms of HEU that's all right together. And if a person fell on the core, you would be very close to critical. So we have things set up such that once you reach that point where you're starting to get too close, where upsets could potentially result in criticality accidents, we have to stop. And this is kind of linked to a rule called the double contingency principle. And basically the idea there is any single mistake will not result in a criticality. It takes two simultaneous independent mistakes to actually get there.
Got it. That's cool. I imagine that makes it very hard to design experiments.
Yeah, and so a lot of the trick in designing experiments isn't really how do I, you know, what is the configuration that is best for the application, which is very important. So we have to start there. But a lot of the hard work in designing experiments is how do we actually build this thing and make sure that we can actually build this thing safely, right?
Yeah, that makes sense. Cool. Well, thank you very much for answering all the questions and for the talk. I'm gonna look forward to going through the slides more closely once the recording's available.
Yeah.
And then thank you to all the participants as well.
And thanks, Michael and Sarah and everyone for inviting me here. This was really fun. So thank you guys.
Alrighty. All right, everyone, have a great weekend and see you soon.
Thanks.